The gradient, the negative gradient.
Okay, fine. So this would be a practice exercise. Yes, to how to do that type of thing. Okay, that's what I want to do next. So at the end of the day, the electric field is the one that is responsible for forces, and many times we're interested in exactly that. So we want to obtain the electric field out of that. So as usual, anytime that we obtain the potential, we compute the electric field by doing this, minus the gradient of V, okay? So that means that we need to do the gradient of that stuff. Okay, so we got that, okay. Okay, yeah, so let's do that, okay. So, okay, so, oh, you want to stop for 5 minutes? No? Okay. All right, so one question of notation, okay, before I continue, is that normally the charge and the separation are lumped together. And this is a very beautiful example of what I was trying to tell you before, which is a little bit difficult concept, and maybe hopefully this will clarify at least partially what I was trying to say. So the combination Q times L is called P. And clearly, of course, it's a vector. It's called the dipole moment. But okay, let me make this point. You will see what I mean. So I told you before, and it's not easy concept to understand, that if you measure effects of charges, maybe the forces that they produce on a probe, it's very difficult to obtain the location of the sources of the charges. I told you that before, okay? Now, this is an opportunity to give you a simpler example of that. Maybe that will help to understand it better. So, the result for the electrostatic potential, and of course for the electric field will be the same thing, doesn't depend on Q and L independently. It depends on the product. And that has an important consequence, because that means that because in the expression Q and L can lump together, that means that if I multiply the charge by 2 and divide the length by half or by 2, then I still get the same dipole moment, and for that reason the same effect on the potential. So for a given Q and L, I get a product, some value. If I divide the Q by 3 and multiply the length by 3, I still get the same answer, right? Okay, so if I don't have an instrument that lets me measure the distance between the charges, then, because it's too small, okay, my instrument doesn't have that resolution, then I won't be able to tell what is the charge and what is the separation. All I will be able to tell is what is the product of them. And clearly there are infinite solutions to that problem. Okay, yeah, so that was sort of...
Why are you okay with those products? Why are you okay with measure that moment, not the charge?
Because let's suppose that they are separated you know, a small distance that my instrument cannot measure. I have a ruler that can go down to 10 to the minus 6 meters, 1 micron, for example, for my instrument, okay, which is a typical thing. And now the charges in a molecule or in an atom are separated by angstroms distances, and I cannot access that. So all I can do is, I will be able to measure the effect. It will have an effect on an optical instrument, it will have an effect on a force sensor, many things like that, okay? But whatever it is, I'm going to be able only to measure the effect of the two together, because I don't have resolution to measure the separation. And so for me, I can make a measurement and I can come up with an answer for P, but not for with Q and L. And it's very typical that people will report values of the dipole moment, and they won't be able with many instruments. So this is a very typical thing. So this is a very nice, simple example of what I was trying to tell you before. If you have a distribution of charges, it is with experimental information many times very, very difficult, close to impossible to get where the charges are and what their values are. Okay, you get their effects, but in different ways. This is an example. Okay, so
what is the benefit? Like, what is the benefit of getting that quality that we can obtain? Being like,
oh yeah, because it's a question of classification. So if you have an atom and then another atom, turns out that they have different P's. And so you can actually, if there's a mixture, different P's, dipole moments.
Peaks?
P.
Oh, P.
Yeah. No, it's okay. And so, if you have a mixture of many different atoms, and you do this experiment, you can detect that there is a P1 and a P2 corresponding to helium and to lithium or whatever, and so you can actually, or at least classify what you have in that mixture. Yes, exactly. Yeah, that's the advantage. Yeah. So even if you don't have access to the charges, the information about P is useful.
But
yeah.
Did you say that L is dependent on Q?
No.
Why?
Well, because it doesn't, right? I mean, if I have two charges, I can control the separation independently of the Q.
In the lab setting, no? Like in the laboratory, you can. You naturally.
Oh, natural.
It's going to do what
okay. But that's a different. Okay. I see what you mean. So
you only find it
no, it's not that the charge depends on it's not that the charge depends on L. What you are saying is correct. Is that for a given material, the charge and L are something.
No, L would be dependent on Q.
No, depending no.
Really?
No, depending
Why?
no. Because there is no connection between the two. They are independent parameters.
I don't see how.
No, but I mean, you have to give me an example. Why the charge?
Like in the scenario, right, just the basic one that you set up for the dipole.
Yeah.
You have a positive charge and a negative charge. In a natural setting, what if they just join forces?
Oh no, but that's a different story. I see what you're. We are talking about mixing a few things. No, of course. Yeah. So. You are asking me a different question now, okay? So the answer to the first question is no. You have two charges, their separation is some other parameter. But now that you are asking me the second question, is good, because it may help to clarify. The length, the separation between the two depend on other forces, not the electrostatic forces alone. So, for example, a very beautiful example that is all around us is water.
Yes.
Okay, water, everybody knows, is two atoms of hydrogen and one oxygen. Okay? So you can make a picture. In reality, it looks something like this. Oxygen, hydrogen, hydrogen. Okay? So the situation in this case is such that there is okay, so you have the center of the nuclei.
So the dipole moment measures the polarity of the bond?
Yeah, but the oxygen tends to draw electrons from hydrogen, and what you're going to end up having is a concentration of negative charge closer to oxygen and a concentration of positive charges here. Okay? So this is a very nice example for another reason, because this is not really the type of dipole that we studied before. It's not a mathematical dipole, because there are three charges here, not two. Okay? But you can argue, and you can prove, that the negative center will be somewhere in here, and this is positive and positive. The positive center is going to be somewhere in here. You can see that intuitively. And then, yeah, and what I'm telling you, once we study the full multipolar expansion, can be shown precisely. But for the time being, intuitively, you have a negative charge here and a positive charge here. The separation, first of all, the charge dependent on the pool of oxygen of electrons.
Yeah.
And the separation depends on other forces besides the electrostatic force. So those two things are independent of each other. But you can argue, of course, given that the water molecule is what it is, the separation and the charge is going to be one particular value for each one. But that doesn't mean that the charge depends on the length.
Mm-hmm.
Okay?
Yeah.
Yeah. Yeah, so, but I'm answering your question. Okay, okay.
Silly question.
No, it's not silly, it's a good question, but...
I didn't really think about it.
Okay, so then we can formally write this way, minus 1 over 4 pi epsilon 0. Okay, then the QL, I'm just going to call it P. Yeah. Sure.
What would you use this type of moment, like value for, other than measuring the polarity of the bond?
So it's yeah. Number one is very used. Like I think Sean was who was I speaking with? Oh no, Kaplan. You asked me the thing about, yeah, so now there's at least two applications that come to mind. One of them is that once you know the dipole moment of different molecules, if you have a mixture of molecules, then you can measure all the dipole moments that exist in your mixture and say this is the materials that I have inside that mixture. So it's a way to study what you have. An unknown material.
Really?
That's one possibility, okay? Second, this is extremely important from a fundamental point of view, because it turns out that later on, when we study dielectric materials, the theory of dielectrics is basically a theory of dipoles.
Yeah.
And so the electric fields that a material like this piece of wood or a piece of plastic produce is all based on this simple model. And so this is very powerful from that point of view. In other words, once you generate an electric field and you put a piece of plastic in the middle, all the atoms are going to behave like this, like with what we just studied. So this is in preparation for later what we need.
Yeah.
Okay, so we still have 25 minutes to go, but I hear people packing, so we should be more excited than that with the class, I mean. Okay, you don't have the ear plug. Okay, okay. So it's okay. So this is the gradient of r minus r prime dot p, which is a constant, over r minus r prime q. Very good. So before I do the next step, what does it mean, the gradient? What is the gradient?
Partial derivative.
It's a partial derivative, is a derivative, okay? And that's the whole point. Is the derivative with respect to what?
Expansive.
Aha. But I just want to make sure that we don't make a mistake, because I have an r and an r prime, which variable should be affected by the gradient that I just wrote? Do I take derivatives with respect to r or with respect to r prime? With respect to r, right? Yeah, okay, why?
Because your operation point can change.
Perfect. Perfect, yeah, exactly. So the r prime is only a label for the location of my dipole. The place where I make the observation point is where I need to make the changes so that I can compute the electric field. Okay, so clear then that when I'm going to do these derivatives, they are going to affect only the r terms. R prime is fixed. Okay, that's one thing. Okay, so now turns out this is a mess now. Okay, and but luckily there is a little bit structure in this mess. There are two vectors. I can actually see two vectors if I want to. One of them is r minus r prime divided by this thing cube. Why not? This is just a number down here, so I can plug it, lump it together with that vector. Dot p. So the structure of what I see here is the following: that I'm trying to calculate the gradient of a vector field f dot G. Okay? So this is type of the problems that we dealt with a few weeks ago. I gave you homework, those type of things. And if you look in the book, there are some so-called vector identities. Okay? And so, okay, this is one of them. Okay? So it's really easy to prove the following. And I want you to pay attention, because this is a recurring theme that comes all over, in this type of calculations, that whether it's the gradient or the curl or the divergence is nothing but a derivative. And so we will see the structure of that. So in this case, there is an identity that I'm going to use, and it looks like this. And there is a little bit of notation that I have to explain. Okay, so what can we do? This is life. Okay, so, all right, so the sooner we get over this, the better. But this is an identity, and look, at least to make things a little bit better for us is to interpret. Okay, so as I told you, every time that we have identities of this type, at least they have a similar flavor. In this case, I have a derivative of a product. You see that? Okay? I mean, in this case, it's even worse, because I have two vectors in here. I mean, it could be that I have the gradient of the product of two scalar functions. That hopefully will be easier. So there are many possible combinations, but doesn't matter. I have the derivative of a product, whatever the details are. And always, look at what we are going to have. It's one of the functions